Welcome to today's Cultivating Success webinar. Today is part 5 of our 5-part webinar series, and we'll be discussing the role of chemical control in formulating an integrated pest management plan. We're really excited that Desiree is back with us this week, and we're just going to do a little housekeeping while people spool in, and then we will share the screen with Desiree. So Cultivating Success is sponsoring this webinar series. Cultivating Success was established in 2000 by University of Idaho Extension, the nonprofit Rural Roots, and Washington State University Extension. We have ongoing programs, and we encourage you to subscribe to our newsletter to keep up to date on future programming and resources that are available through University of Idaho Extension and the Cultivating Success program. We are in webinar format today, so Kate is standing by. If you have any troubles with your sound, your speed, go ahead and type in the chat and we'll troubleshoot whether or not that's on your end or on our end. You can always switch to sound by using the up arrow by the audio in your control bar. At any time during the webinar, please type questions for Desiree into the question box or into the chat box. We are recording this webinar, and both the webinar and the slide handout will be available on the Cultivating Success website. We wanted to start out today's webinar by launching a poll and just getting a read on what your level of understanding of the role of chemical control in integrated pest management is. So you should see a poll on your screen and be able to answer this question. How familiar are you with the role of chemical control in IPM? And then our second question is, how confident are you about implementing an integrated pest management plan? You can see about half of our participants have answered the poll. We'll give that another few seconds. So I will go ahead and give it one more second. We have a couple more people that are still answering. Sometimes it takes a little bit longer to answer on your phone than on your computer. Okay, I'm going to go ahead and end the poll and share the results. So we have a lot of familiarity with this cohort on the role of chemical control in IPM. That's great to know. A couple of folks feel somewhat familiar. And then we have almost 50-50 on whether or not people feel very confident or somewhat confident in implementing an integrated pest management plan. Okay, that's a great read for the start of our webinar. So again, we are really happy that Desiree Wickwar is available today and able to lead our final webinar. Welcome back, Desiree.
Thank you. I'm excited to be back. Once again, I might turn off my video if my home internet goes wonky, but we'll give this a go for now. All right. So just to take care of my little bit of housekeeping, real quick, if you are here for pesticide applicator credits, just a few reminders on what that entails. You have to have entered your Idaho applicator number correctly in registration, and you primarily have to have been present for this whole webinar, and I have to be able to see your name on our roster. So if you end up calling in, maybe shoot something into the chat or shoot Kate an email so I can make sure we get that figured out. But we haven't had problems so far. So, all right, moving on. Okay, so I won't be belaboring the idea of what IPM is today, but I will talk about the role of chemical control, and hopefully by the end of this, you guys will have started formulating your own IPM plan for a system that you select. So, since I haven't been here in a second, I'll reintroduce myself too. I am the University of Idaho Integrated Pest Management Program Manager. My background is in entomology specifically, and insect management. And that's kind of my bent. But I also help coordinate our pesticide safety education program. And so this is a topic near and dear to my heart. Okay, so like I already said, this is kind of our itinerary for the day. First, I'm going to talk about some chemical pest management. Just these general ideas, general practices. I'm kind of excited to see that we have some familiarity with this topic because I'm not going to be going over just the basics, maybe what you would hear in, an intro course, but maybe some little nitty or grittier topics for us. Um, then we'll go over sort of a combined case study and exercise where I'm going to ask you guys to either on paper or in your head work on creating your own IPM plan. Okay, so reminder, since we're talking about chemical pesticides specifically today, a pesticide is any mixture or single substances that is meant to do all these different things. Prevent or destroy, repel, mitigate a pest, can be even used as a plant regulator, a defoliant, a desiccant, and interestingly, or a nitrogen stabilizer. So this is for regulatory purposes, and I think this is relevant as we're trying to remind ourselves because, maybe in the biological control webinar, we're reminded that technically, applying something like a living organism like spinosad, that is technically a pesticide. But would we call it a chemical pesticide? And there's subtle differences, and especially when you're reading literature and trying to figure out the exact dynamics between management techniques. I think just important little reminder to think about our terms here. So we're going to be talking about the top of this pyramid that you've probably seen a few times by now. As a reminder, this doesn't mean that IPM precludes the use of chemical pesticides, but we are going to view them as like this height of corrective measures in our system. And we're going to use them accordingly, just like we put them at the, things we use sparingly at the top of a food pyramid. We try and use them sparingly because they can have some tricky outcomes. But that's what we're going to talk about navigating today. Little background on pesticide use in the United States across time, because I think this is both interesting and informative as we think about the pesticides we use. So on the left side of your screen, you're going to see a little pie chart that shows the most commonly used active ingredients in 1968. And these adjacent to the key you're going to see a little H or maybe an I in parentheses. H is herbicide, I is insecticide. These are going to be primarily the ones we're concerned with here. So what you can see is in 1968, the top active ingredients were herbicides and insecticides, sort of in an equal mixture. When we look at the history of pesticide use, insecticides came into common use, at least in their chemical form. Insecticides came into use much earlier. But what we start to see is a pretty significant shift. This study just went up to 2008, so a little bit old data, but I think this pattern has probably continued to hold true. Then now what we see is primarily a lot of herbicides being used, and we'll actually get into a little bit of why that might be later. But yeah, so there have been significant shifts over time in what we rely on most heavily. As we're thinking about how pesticide use has evolved, I think it is important to remember the role of the manufacturers in this. So when a manufacturer launches a pesticide into the market, they are responsible for conducting a wide variety of tests. They're going to get at topics like toxicity. Can be, for non-target organisms, and the environment, the general effect that this might have on people, these sorts of non-target effects, the efficacy. So that's going to be how effective is it at actually killing all the target organism it's going after? How does it degrade in the environment? What's the speed of that? What does it degrade into? That kind of gets into mobility and residues as well. What's left over after we've gotten what we want out of that compound? Here is a question for you guys. If you're feeling excited, you can put a number in the chat. What is the approximate dollar value that you think it might cost a company to bring a new pesticide to market? You can give like a greater than, less than, totally loose answers here. I see a 10 million. And I should say this is any new pesticide, not necessarily an active ingredient. 10 million, 200,000, greater than a million. Okay, so at least I'm already seeing big numbers, right? I guess we probably would expect nothing less of these big companies, but generally, what we're seeing is about $400 million. So a big chunk of change. And a lot of this is R&D, but this is primarily a reminder that though we're being really conscientious when we're using pesticides, manufacturers are required to do a lot of work. And this is me saying that you should lean on all of that work. Because that all that information that they spend $400 million producing goes into making a pesticide label. I know they're a giant pain in the butt, and you've probably heard this a lot, but this is the one simple point I will belabor, is that when in doubt, I genuinely believe that it is worth your time to read a pesticide label. Not only does it protect you, it protects the organisms that you're treating. You know, maybe that's a plant, or maybe that's you're applying a chemical pesticide to your dog. And of course, protects the surrounding environment, groundwater, all of these sorts of things. So before you buy a pesticide, I would say read the label. So before storing it, know that you can either get toxicity from incorrect storage or you can have your pesticide go bad, waste some money. Before you mix it, there are some plethora of horror stories about people mixing active ingredients that are not compatible, and it can either really do a number on whatever organism you're applying it on, it can ruin equipment, all sorts of negative impacts. It can have really weird chemical reactions, of course, like produce extreme heat. None of these things are outside the realm of possibility. But if you do your due diligence and you read the label, you, you can avoid these things. So with that, I will talk about kind of what I was saying. We're going to delve into maybe some more complex topics surrounding pesticide use, not just me belaboring the point about a pesticide label, which you've probably heard before. I want to talk about what we sometimes call the 4 Rs, this pesticide treadmill that we end up on. And so we're going to talk about pest resurgence, replacement, resistance, and residues. 4 Rs. Okay, first, resurgence. What is this idea? Resurgence occurs when a pest population that you're targeting is actually reduced, but then it rebounds to the same density or higher. I'm an entomologist again, and I have soft spot for spider mites, so great example is spider mites. How exactly is this happening? So let's pretend this leaf is our little case study. What we have is a number of pests and a number of natural enemies. We look at this and we say, oh shoot, that's too many pests. They're causing too much damage. So we spray. What happens? Predictably, we do have some reduction in our pest population, but we also have a significant reduction, in this case, 100% reduction of our natural enemy population. One common scenario is that natural enemies prove to be more susceptible or can be extremely susceptible to our active ingredients that we choose to treat a pest if it's any sort of broad spectrum. And I'm leaning on insects in this example, but there's truth in this in microorganisms as well, like fungi and bacteria. So then resurgence happens. So we went from having these two little pests to having a bunch of them over again. Why is this happening? Well, first off, of course, like I mentioned, destruction of natural enemies. So what happens is you have all of your natural enemies removed from a system. So the way that they were sort of trying to keep that pest population down, that's no longer at play. So that can be either through direct toxicity, that is, your spray is directly killing them, or what can happen is even if they're not directly impacted by the spray, they can either starve or leave the area because when you spray, you have completely wiped out your pest insect population, which was also their food. So sometimes they either perish for lack of food or they leave the area. There can also be interesting phenomena where what happens is when a pest is sprayed with an insecticide, this is true of insects, they will have this physiological response that says, oh no, I'm dying. And therefore, I'm going to really increase the rapidity of my reproduction to get my offspring out into the world. Basically, it's you dump all of your resources into producing offspring because that organism senses its imminent demise. So that's something we can see with certain chemistries. If you think that this might be happening to you, I would say research this phenomena because it tends to occur with certain chemistries, certain active ingredients, and certain pests combinations much more than others. Replacement. You might hear this called a secondary pest outbreak. This is number 2 on our R's. Um, what happens in this case is a secondary pest. Sometimes it can be a pest that wasn't really that economically or aesthetically impactful in the past, replaces the pest that you targeted with a spray. So that pest is gone, and it is replaced by this new pest that used to be there in small numbers, but now comes back really hard. So what that looks like, in this case, what we have is let's pretend these blue guys here are our main pest, little yellow guys. We just have a few of them, not really doing that much. They're a minor pest, they're out there, but it doesn't really matter. And then we have our scary looking red natural enemies. We spray, we say, okay, cool, this has reached an unacceptable level of damage. We got to do something about it. We spray. Um, what do we think happens? Naturally, the natural enemies go away for those reasons that we just talked about. A lot of your target pest population will disappear. Especially if you choose a specific chemistry targeting them, or sometimes they're just more susceptible to whatever tactic at whatever time because these are the ones you're after, right? So looks like we did a pretty good job of removing those, but problem, we left a ton of space, a ton of available resources for this secondary pest, which used to not be that abundant, to come back. And then sometimes what we see is that pest that we never used to really think about becomes a significant problem. We actually see this sometimes when certain chemistries are removed from a label. So let's say, or are removed from use in a particular spectrum, heavy duty compound that has a long residual at the beginning of the year, every year, to control aphids. And suddenly that goes away. Well, what we might see is that the aphids outbreak more significantly than they have in the past. But then what we might see is that things that we didn't really ever consider in the past, maybe it's a specific caterpillar, comes into play because that used to just be sort of a side effect of the big broad spectrum we were spraying early in the season. But since we're no longer using that particular spray, that secondary pest or really non-economic pest can become more impactful in our system. And this can happen for a number of different reasons. I'd be really interested to hear if anyone has ever experienced this, where, one year you just have some weird weather phenomena or a change in your cultural practices, and a pest that you've never really had to be concerned about becomes a problem. But replacement can be one way in which that happens. All right, resistance. This is, of course, a big one when we are considering a pesticide application. So, resistance, what exactly is it? When we're referring to this in a pesticide system, we're talking about a heritable, that is genetically derived or genetically predetermined ability of a population to survive a insecticide or any pesticide dose that would be lethal to a normal population. That's how I think about it. So basically, how much of a population can survive when it's sprayed? How exactly does this happen? Well, the big one that we oftentimes worry about when we're talking about insecticide or pesticide use is repeated use of the same mode of action. This is one we've probably all heard of, right? Like what we want to do is we want to alternate active ingredients and alternate different modes of action. Because what happens when, let's say, we spray this population, this red guy, he is totally fine. It kills the vast majority of the population, but the one red one is totally fine. Again, he has a ton of space now. And so he goes forth and multiplies, and suddenly that spray is no longer nearly as efficacious as it was in that first instance, right? Because all we have left after spray number one is the resistant individuals. And then they go on to pass that heritable trait on to their offspring. So what we see is an increase in the proportion of a population that's resistant over time. And if you can imagine only using the same active ingredient or the same mode of action over and over, that becomes our primary selecting factor for who survives in that population amongst the pests. If we kind of have alternating pressures, say you alternate different modes of action, sure, you might select for one resistant population with your first spray, but hopefully, and often, what will happen is then you switch to a different mode of action, and then that same population that survived the first spray is no longer resistant to that second one that you use. One of the reasons behind this is what we kind of see, and this might be more familiar for us in plants, but what we see is that resistance traits can be what I would think of as metabolically expensive. If you are spending all of this energy producing proteins or having traits that can help you resist a certain insecticide, you're spending energy on that. So individuals that, because you might say, okay, well, why doesn't everyone end up being resistant to everything? Well, that could certainly occur, but that ends up being really expensive to produce a ton of different resistance traits. So in general, that's why rotating modes of action is effective. We'll go through some specific mechanisms of exactly how resistance happens. This can get a little bit into the weeds, but I think it's useful to know about. So, a few different ways that pests can go about being resistant, and believe it or not, this actually does go for things other than insects, is behavioral resistance. That can be, something like during a certain time of the year when you might usually spray, or given certain cues, an organism will adopt a different behavior that sort of shields it from a pesticide. So what we see in this instance is the example of avoidance, maybe. Maybe this aphid sort of has a higher um, uh, sensitivity to vibration. So when you go out to spray, they, drop off. They aren't contacted on the plant, and then they climb back up the plant. General example. Population growth can be one. This can be this idea that you're selecting for individuals that have really fast generation time. They're just really reproductive. Their genetic traits make them reproduce very quickly. So that can end up manifesting itself as a certain form of resistance. Biological resistance can be another one. This is sort of alterations in the organism's life cycle that help it to resist a target insecticide. So this can be certain things like those organisms that undergo asexual reproduction have less opportunity to have mutations and different genetic recombinations occur such that new resistance traits, those kind of genetic ones, pop up in a population. Whereas in sexual reproduction, there's this combination of a bunch of different genes. And traditionally, what we see is those organisms are able to evolve resistance more quickly. When we get down to the genetic level, what's happening when I say, there's these mutations that are more likely to occur in certain populations because of their life cycle or their traits? What exactly is happening genetically or metabolically that's causing insects to become resistant? Well, target site resistance is one of them. So, for instance, let's say we have an insecticide that tries to target a specific synapse in an insect's body. We might have things like certain insecticides will cause insects to be unable to have basically their muscles fire. So if that target site is no longer susceptible to the chemical that blocks it, then we would no longer see any efficacy of that insecticide. So target site resistance at the sort of neurologic level. Penetration resistance can be one. Cuticles, so the exoskeleton of an insect, could be altered such that if it builds a really thick cuticle, then it might not actually penetrate into the insect's body. You know, if this is a contact insecticide, then what we might see is just change in cuticle thickness over time that over time induces a level of insecticide resistance. Metabolic resistance can be one. Basically, like this is the idea of the development of different enzymes that would break down these compounds. So the target site still exists, maybe, that would cause this insect to be killed by an insecticide. And the insecticide does get into its system, but instead they have some ability to break it down before it actually causes their death. This can kind of occur in two different ways. So we can have an enzyme break down the toxic molecule, or we can actually have microbes that are selected for in a population that break down that insecticide molecule such that it's no longer effective. And you can see how, so there's sort of two levels of selection here, right? We're selecting for certain traits in the insect, but then we're also selecting for insects with a certain microbial community. Kind of an interesting little factoid. So, one thing that I sort of vaguely alluded to earlier is there are different forms of resistance. We hope not to see these really crop up. But sometimes what we see are both cross resistance and multiple resistance in different populations. And since these are terms you might kind of see and that I do think impact your management decisions, I wanted to define them here. So, cross resistance is resistance to pesticides with the same mode of action. So that's why we're not just alternating active ingredients necessarily, but we have to also keep an eye on the different modes of action, because, you know, many of those mechanisms that we just alluded to have more to do with the active or the mode of action of the insecticide than its brand name. You know, the insect doesn't care about that. So that's what we, excuse me, are referring to when we say cross resistance. Multiple resistance is a scary one. And this is one that you're probably more familiar with in weeds, if I had to guess, and we will talk a little bit about that. Multiple resistance occurs when a pest is resistant to different modes of action. And this is a scary thing that usually takes longer to crop up, but is much more difficult to manage. So when I was talking earlier about rotating different modes of action, so different ways in which, you know, a pesticide might target something metabolically or physically, um, this can be more challenging the more forms of resistance you get at play, right? Because we only have so many compounds that are registered for use in our crop at a particular time that are economically feasible. So as soon as we get multiple resistance forming, management can become exponentially more challenging. What has this looked like over time? Unfortunately, as we introduce more and more compounds, and they become more accessible, more widely used, what we see is that resistance and multiple resistance has increased a lot. So what you see in these graphs is on two different timescales. But what you see is the increase in glyphosate-resistant reeds worldwide on the left side, and the number of resistant species for a bunch of different sites of action on the right side. So what we're generally seeing, right, is in general, particular when we look at weeds, the number of different species that are glyphosate resistant has just massively increased since we first started documenting this in around 1995. And like I said, you know, if we become really reliant upon one compound, something like glyphosate, especially when we don't have that many herbicide chemistries at our disposal, this is what we see. And now you can see every single point on this graph is a weed that has some documented population that had become glyphosate resistant. And here in Idaho, I am sure that many of you have heard of our increasing problems with different weeds becoming resistant to glyphosate and a number of different compounds. So this is something we see very often. Residues. So last but certainly not least, um, exactly what happens to a pesticide when it enters the environment, and how is this altering how we choose what we use, and how we move forward. This will let me advance. Um, so the ways in which this can happen are multitudinous, but a few that we'll talk about today are this idea of bioconcentration, bioaccumulation, and biomagnification. These all have to do with what exactly happens to a pesticide in the environment, but they do mean different things. And again, since you see these terms, I think it's important that we go over them. Bioconcentration is the first one. As the name sort of suggests, what this entails is increasing concentrations of a chemical being stored within the body of an organism via direct uptake from the environment. So, what that might mean is that um, a a quintessential example might be organochlorines. What happens with them is they are consumed by an organism, and they're what we call like heavy compounds, or they're really not easily metabolized. And so what happens is they get stored in the fat tissue of individual organisms. Bioaccumulation, subtly different. This is increasing concentrations of a chemical within the body fat of an individual organism via uptake from food. So you'll notice that bioconcentration from the environment, bioaccumulation from food. Um, and what that means is that, let's say something eats an organism that was having um, its own load of a certain toxic compound, then that organism gets, kind of a double, triple, quadruple dose of that compound that had already been accumulating in that food item, that other organism for its entire life. And then that can't be metabolized by that organism, that predator, and then it's stored in the fat of that individual as well. Biomagnification is essentially this on a large scale. So what we get first is uptake from the environment. Let's say that a primary producer, a plant, accumulates a bunch of a compound. Then we get the next level. We get something that eats that plant. Well, it accumulates all of the different toxins from all of the different plants it ate. So you can imagine we're stepping things up. And then something eats that herbivore, and then something eats that organism, and then so on and so forth. So what we see is as we go up the ecological food chain, kind of increasing in our trophic levels, we get more and more of a toxic compound accumulating. It's something why, sometimes we hear like certain ocean fish, like maybe tuna, for example, they have really high levels of heavy metal. You can imagine that this is because they are way at the apex of their ecological food chain. They might be eating um, predators that were eating predators that were eating predators. We might call that, like a tertiary consumer, for instance, if it's four tiers up the predatory food chain. So, that's just to relate that to something that we hear about sometimes. Okay, so what exactly do we do about this? Particularly when it comes to resistance. I bet many people have heard of these, but we have these resistance, um, these ideas of different modes of action Of course, I'm biased towards the insecticide ones, but we have them for herbicides and fungicides, these different ways that compounds go about actually causing the death of a particular pest. And we group them into the ways, if you remember back to those modes of resistance diagrams, exactly how is this going about metabolically killing something? That's how we're grouping these things. And then what we try and do is then alternate between as different as possible modes of action to kind of avoid the development of resistance. And one thing I will say is that resistance is something that it's easy to think about on a small scale, right? It's easy to think about this as I need to alternate modes of action in my system because I need to be able to control my pests. But what we also, I think, should remember is that this kind of has to occur on a community and landscape-wide scale in order for it to not impact all of us. If your neighbor is not using resistance sound practices, you are probably going to get some drift of the genetics of their pest populations into your system, and then all of your good work alternating modes of action will be for naught. Um, and yeah, it's kind of the responsibility of all of us to be aware of this. Okay, so without further ado, what I want to do, well, I guess I can take some questions if there are any first. I haven't monitored that. Let's see. Can't even see the Q&A. Well, I'm going to, since I don't want to leave my presentation, I'm going to say we'll just address questions at the end. Okay, so yeah, without further ado, what I think we should do is run through a case study and get you guys formulating the general outline of your own IPM plan. You might not come away with something that is fantastically detailed and you know exactly what you're going to do on every day of the year from this, but I hope we can at least get everyone started. So what's going to happen is I'm going to pretend that I'm going through this exercise for an apple orchard. So I'll talk about, kind of what I would be considering as I was writing an IPM plan, pretending I own a small scale but commercially um, producing apple orchard. Okay. You probably remember this from many of these different webinars so far, our discussion of how important monitoring is. In our diagrams, when we talk about IPM, we always say monitoring's first. So that is what I would consider first, is monitoring. I guess in some ways, easier said than done, right? Because you're like, well, okay, what do I do exactly? What am I looking for? So first, to figure out exactly how you want to monitor and when, what you need to do is make a list of the common pests for the crop that you're looking to monitor. So again, maybe what you can do in this instance is think about what's a crop or a plant or a system that you are interested in making an IPM plan and sort of either write this down as we go along or just kind of think about it. So what you do is you'd think to yourself, okay, what are the pests that are common for this crop? And, another thing I might add is what are the pests that you have observed in the area in the past? Especially if you're working with something like an apple orchard, which is, consistent year after year. But even if you're working with, maybe a garden or a field crop that is rotating, what has been there in the past? What might it possibly be able to do in this new system? If you're rotating crops, of course, there are going to be some specialist pests that are just no longer going to be relevant. Maybe you had some aphids in your wheat one year that are grass specialists, and then next year you rotate sugar beets. Well, lucky you, you don't have to worry about those grass specialists anymore. Even though there's probably some of them in the soil, they're not going to have anything to munch on when you're just working with sugar beets. One thing I did want to do, I'll stop sharing just for a second, and we'll bop over to the P&W handbook. So if you're not sure what pests you should be looking for, this is one place where I would think to start. So let's say you're like, well, I sort of know what I've been seeing out there, but what are some other ideas? What I would do, let's say I am again working with Apple. So what I would do is I would go to the P&W handbooks, and I'm remembering to put this in the chat. Uh, So I put that in the chat if you guys want to kind of play along. So what I would do is if I'm saying, okay, exactly what pest should I be worried about? I want, as a reminder, I want to find things that are P&W specific, specific to my area. So a great resource for this is the P&W handbook. What it does is it collates expert advice from a bunch of different people at Washington State, Oregon State, and University of Idaho. We kind of come together every year to write an absolutely astonishing variety of information on pests and pesticides that are relevant in the Pacific Northwest. So, again, my bias is insects, and in the interest of time, I'll just run through what I would do for insects for my IPM plan. But note that in the P&W handbook, you can find information on plant diseases as well as weed management. But back to this idea. So I'm trying to think to myself exactly what should I do or what should I be looking for apple pests. So I would click Apple and say apply. And here is what I find. Under this first heading, where it's saying apples and apple pests, this is every single pest that has been listed as a potential pest of apples in the P&W handbook. I know this is a very long list. So, you might see some familiar names and be like, oh, okay, right. I totally remember seeing scale, or I totally remember seeing spider mites. Some of these are going to be major pests. Some of them are going to be minor pests. But if you're looking for a starting point, you can kind of peruse this just to get an idea of what you might be seeing. Okay, back to my other presentation. Okay, so what would that look like if I was to do this for apples? Let's pretend that I was like, well, I've had this apple orchard for a little while, and in general, this is sort of what I see. I would think to myself, okay, what's the most destructive pest? Maybe it's codling moth. That wouldn't be unlikely. It's a big concern of ours, right? So I would kind of think to myself, okay, this is when it causes damage, this is how it causes damage, and how much. Thinking about, its natural history, what time does it emerge? Maybe for aphids, you're also considering virus transmission. So this is sort of the list that I would make for myself of things I want to keep tabs on. Okay, so I know what I'm going to keep tabs on. Then what I need to do is determine how I need to keep tabs. This one has to come second, of course, because different things are monitored in different ways. So, degree day calculations are a great one. We've talked about this in a webinar in the past. If you don't remember, I think those are recorded, so you can go grab that. You could kind of get an idea of about when are these pests going to become active? When are they going to become damaging? If they do reach damaging thresholds, when am I going to have to treat them? So you can get an idea of when to start monitoring and when to really key in on your monitoring if you're nearing a time where treatment might be recommended. So that's that's kind of how you can know about when to monitor. How to monitor is a different consideration for you. I imagine that a lot of you monitor using some method already. Maybe that's just walking your fields or walking around and checking out what's going on in your plants. Obviously, a completely valid way of monitoring. We talked about this a little bit in our first webinar. Monitoring can be things like looking for the pest, but also don't forget to look for just signs of it. Maybe sticky residue from sap feeders like aphids or psyllids, or frass, or entry holes, or all these different things. So just remember to be thorough in that. Sticky traps and pheromone traps are also ones that I pulled as kind of ones that I think of in orchard settings specifically. Um, you can use these baited or unbaited to just attract different organisms, so they're kind of working for you while you're not in the field. You know, if you're just doing visual monitoring, you might struggle to see certain really small pests or really well camouflaged pests, but these traps are a great way to do it. For certain other crops, you know, we have aids that are created by the University of Idaho, like a spore monitoring network in the more southern part of the state that says, okay, you know, spores of such and such disease were found, or you know, we might have pitfall traps for insects that are ground dwelling. You know, these aren't as commonly used in something like an orchard, but as you peruse the P&W handbook, there's usually a blurb on monitoring, or if you're not finding ideas, at least you can look up specific monitoring tactics based on the list of pests you create. So think about how you're gonna monitor. Think about it logistically, what makes sense for you time-wise, given what you kind of think the timing of your monitoring needs to be, the duration of monitoring. Some pests you have to monitor from the minute the plant comes out of the ground to the moment that you harvest, or the moment that the first frost happens, or something like that. Some monitoring periods can be extremely long. So take that into account when you write your monitoring plan. You know, you don't want to say, I'm going to monitor 3 times a day, and then lo and behold, you have to monitor for 6 months. So just keep those things in mind. All right, this is another one we've talked about, and so I'll lean back on our more involved discussion of determining action thresholds. But what you're going to try and do, of course, is once you start monitoring, you need to do something about your findings. You're going to determine how many of a specific pest you have around, and leaning back on that information that you wrote in your initial list. How damaging is this? How much economic damage can it cause? You know, when does it cause the most damage? Is that really concerning? Leaning on that biological information for the pests, as well as published thresholds where you can find them, determine what your plan is for different damage levels or different pest levels. The numbers I have given here, don't take these as gospel if you have an apple orchard. They're just sort of vague numbers I pulled from different pubs, and they might not be exactly accurate for our area. I apologize for that. Um, but, you know, what I would try and do is kind of go peruse the literature. You know, there are some ideas in our degree day models, like we talked about in a previous webinar, that might help you with that. You can contact extension agents to ask them if they know of any, you know, local or reliable resources, to find some rules of thumb, or when possible, an exact treatment threshold. All right, let's say we have decided we met our treatment threshold. What we're then going to do, of course, is select amongst our treatment tactics. Ideally, what we're doing is we're formulating this plan a good bit in advance of the season. So what you might say is, okay, well, you know, I know that aphids are going to be a problem for me this year in my strawberries. So I'm going to use a reflective mulch. And that's something you're going to have to know right when you're planting, right? So you might consider something like that. Of course, I guess back to my orchard example, something you might be saying is, okay, I need to remember to remove fallen apples and fruit debris before anything might have the chance to emerge out of them, because there's probably some critters overwintering in there that I don't want. So sanitizing the area. Planting trap crops would be another one that would require a little advance notice. So just think about the cultural practices. In that P&W handbook, which I'll go back to here in just a second, there are usually recommendations or some general ideas for cultural practices as well as chemical. Biological control, of course, another one where just consider the needs of your system. If you're interested in using it, you can get in touch with someone at UI, or consider talking to a purveyor of natural enemies to kind of pick their brain about what's been successful for their clients. Talk to your neighbors, talk to your friends, all these sorts of things. And consider your non-chemical tactics. But then, of course, we're going to consider our chemical tactics. And again, I'll lean on the P&W handbook for some specific chemical recommendations, and I'll go show you what that looks like in just a second here. But some reminders when you are choosing amongst different chemistries. Remember back to that list of pests you made. Remember back to which pests actually cross the treatment threshold. When possible, um, especially in a high dollar system like an orchard or a specialty crop, you are probably going to want to pick the most specific pesticide possible for the species you're looking to target. So it doesn't harm beneficials, and so you don't get some of these other issues that arise. Considering the environmental impact is, of course, ideal. What you want to do is kind of read into that label, do your due diligence on understanding the implications of using this chemistry and using it correctly to minimize the um, environmental and health impacts of its use. And that might even include things like making sure you're not running into a pre-harvest interval where you can't apply certain pesticides close to when you would like to harvest a crop. Resistance management, we talked about this one a little bit, but like, let's say last fall, I just used one chemistry. I might really strongly consider using a new one this year because that same genetic population, or I might consider not using that same mode of action this year because that exact same genetic population is going to be a lot of the ones that have overwintered in the orchard and are going to emerge again. So what you might be doing is then applying the same mode of action over and over again, selecting for just those individuals who can resist it over time. And then you might kind of run out of tools as time goes on. Once again, I'm going to briefly go back to the P&W handbook. And we're going to look at, it's my favorite pest to talk about during this webinar series, apparently. So let's jabber about what you would use or how you'd use the recommendations in the P&W handbook for codling moth. That's our big pest, right? So, like we said in our initial list, what would I do? Well, let's say we run through this, we can kind of get an idea of what the pest looks like, helping us to identify it during monitoring, its biology and its life history. I would read through this. And then there's this whole section on how to sample and how to determine if a threshold has been met. You can see it already is referring to degree day models, biofix dates, all these things that we've already talked about that hopefully are providing you tools to most effectively use recommendations like this. So we understand the identification and biology of the organism. It's helping us run through ideas for how to trap using maybe pheromone lures, for instance, exactly when to be trapping, and then always to then eventually determine if a treatment needs to be made. So then what we're going to get is into different forms of management. Like I said, this is going to provide some ideas for cultural control, for biorational control, and then importantly, for this last consideration of ours, we're saying we got to use chemicals here. What do we do? These publications will often be split into home use and commercial use only, so make sure you're looking at the right section. And then what we get is some general information on when to apply. Of course, you want to consult your label as well to make sure you're timing your insecticide application correctly to target what phase of a pest that you're looking to target. But then, so here's going to be what is currently registered for home use for codling moth in the Pacific Northwest. And I should say these are updated annually to reflect changes in registrations. And you'll find the same thing for commercial use with some guides on reentry intervals and timing of applications and all those usual bits and bobs. So yeah, some really useful information. As you can see, there's a ton of it here. And for a truly impressive number of pests. Not every pest is as thorough as that codling moth profile. Some of them will be a little bit shorter, but it's a really, really great resource. And I think with that, Oh, no, not with that. Of course, after we're treating, we're following up with additional monitoring. We need to know how effective we were in our spray. You know, ideally, we're timing things perfectly, but if it was a little off, we might have resurgence. We might have a secondary past outbreak. We might have any of these things. We might have unknowingly had a resistant population. So remind yourself to follow up after your treatments. Just because you treated doesn't mean you get to sit back and relax, unfortunately. There's still things going on in your system, and you still need to keep in touch with them. And with that, actually, now I can take questions if there are any. I'll go ahead and stop sharing.
Desiree. Let's see. I see that early on, Melissa put a question into the chat. I think she was wondering if there were some factors that apply specifically to organic pesticides or all pesticides are pretty much equal.
Yeah. Um, I imagine this is in reference to like our 4 Rs of our pesticide treadmill. Unfortunately, just because something is organic doesn't necessarily mean it's not going to be subject to these exact same rules. Bioaccumulation is certainly documented in, maybe like I said, there's bioaccumulation of heavy metals that have nothing to do inherently with pesticide use in like tuna. So sadly, a lot of the same rules do apply to organics. It can kind of depend, right? Like if we're thinking about like, oh, spinosad, that's organic. It's a biological pesticide, but it is a pesticide. Um, some of the same rules could still apply. If you're only using spinosad to control a population, you might get certain levels of resistance developing. Great thing about, some of these biological products is bioaccumulation, not as much of a thing, biomagnification, all these bigger, scarier ecological consequences. Um, but a lot of the same rules still apply. Some organic compounds are like a heavy metal, um, and very much subject to the same rules.
Thank you. Thank you
Good
for your
question.
presentation. I think we're going to do our concluding poll. If anyone has any other questions, please go ahead and type them into the chat and we will follow those up after our last poll. So we have 2 questions. After participating in this webinar, how has your knowledge about the role of chemical control in integrated pest management changed? Has it increased, no increase, moderate? And then after this webinar, how has your confidence to implement an IPM plan increased? We'll just give a couple seconds for people to continue to answer that question. And while we're doing this, Desiree, do you want to just review one more time how the pesticide credits are going to work for today's webinar?
Ah, there it is. Not at all. So essentially what will happen is everyone who registered for the webinar today should have had to enter their pesticide applicator number. So basically what I will do is I will take that applicator number from your registration and I will match it with our little Zoom roster that says who was present and for how long today. And as long as you registered and were present for the whole webinar and you entered your number accurately, I will enter those probably right after this webinar. And as soon as ISDA approves that whole process, they should be live on your accounts at ISDA probably today or tomorrow.
Thank you. Just to recap on our poll, it looks like everyone who participated today indicated that they either had a moderate or a significant increase in their understanding of chemical control in integrated pest management and their confidence to implement an integrated pest management plan. So thank you so much, Desiree, for your very impactful and detailed presentation showing us the PNW handbooks tool. And just a reminder, everyone, if you want to review this information, both the webinar recording and the slide handout will be posted on the Cultivating Success website. Thank you very much. This concludes our Spring 2025 Cultivating Success webinar series on integrated pest management. At any time, if there's other topics you would like to see covered, please reach out. You can contact any of us through the University of Idaho webpage or directly through Cultivating Success. Thank you again and have a great rest of your week.